In this section, now we move forward with the input parameter that you saw on your slide. Now we have input parameters, then declaration of the variable in a program, and we are following the specification as well as standards in Fortran 90 and 2000. So we are using the syntax of this particular programming language. Now, as soon as you give parameters, first thing the program does in a computer world is that it opens files to read some of the input parameters. So, in data is the file that is already given to the computer in the same directory structure. It is formatted, so it will expect particular kind of format that is specified in the open statement, and this is assigning the file units. So, these are the 4 file units that it is reading. It's looking at creating a file unit in data and reading that. MD out is going to also create a file so that it can put all the data out with certain headers. This is giving the initial positions, and then it is also giving you position 1 after you have finished. So, it is also going to update positions of the particle as you calculate the particle trajectories. So, every 100 time step it may spit out and put in this particular file unit 4 position of the particles. So, now let us say for some reason your computer failed, you already have this position file, you can start your computation from that position. So, you do not have to restart again, and in some cases the positions of the particle at the end of each molecular dynamics run is kept, so that next time when you do that equilibration phrase, you do not have to go through that because you already ran that, let us say 10,000 time step. Now, you will start always with that time step, unless you want to look at equilibration one more time. So, it assumes that you have equilibrated the positions. Now, going forward comes back to the same idea. I am trying to now bring you back to what we talked earlier, is that the time step. So, we have to use the time step delta t small enough to model the vibration of atomic bonds correctly. So, now we are looking at this situation where we have to decide what is the time step in terms of femtoseconds. So, we are going to create each time step as few femtoseconds, 5 femtoseconds, etc., and then integrated the predictor corrector into that time steps and generate the positions for those time steps, and then keep going. And after every 5 time step, as you saw earlier in VMDL simulation, or 10 time step, we are going to do the calculation of the force, etc. So, in this case, set the time step in terms of our molecular dynamics code. So, we find out the potential cutoff, neighborless cutoff, and cell size, etc. So, we are looking at RC as 2.5 sigma. We are looking at cube size volume to the power third, and you are looking at cube, and you are looking at half of the cube size. So, we are creating the R list. So, we are essentially setting up parameters so that if you look at RD max, which is half of the cube size, we are looking at that and create for the periodic boundary condition. We are also looking at the list. Now we are creating some logical statements like if R list is greater than RD max, then R list is equal to RD max, and if it is RC, which is the cutoff radius, is greater than cube 2, then RC is equal to cube 2 minus 0.35. So, this is how you are working inside the box with different kinds of R factors, which is the position vectors that you are looking at, and you are saying that R max, the position vector max in this case, is square of the RC, which is sigma multiplied by sigma. In this case, it's 2.5 sigma, so it's 2.5 sigma multiplied by 2.5 sigma. So, this is how you set up the maximum length scale that you are going to use. Now, in terms of time, you are looking at delta is equal to 0.005, and if you look at delta square, the time square, because you have to do time square, then you have multiplication of that, and the delta square root, we are looking at time square root. So, now you are also creating the half of that, and then t step, which is the time step, is becoming in terms of the mass of the atom, and the sigma, which is the interparticle distance. If you remember, in our previous slide, we looked at it has to connect with the bond length, and in this case bond length is sigma, plus you are also looking at vibrational frequency, which is coming out of epsilon. So, if you look at time step is then decided by this equation, and is to e to the power plus 12. So, if you look at this, we are looking at the time steps which are very, very small, e to the power minus 12, which we are looking at the time span which we are looking at femtosecond scales. So, now if you look at that, now we also want to do velocity rescaling. So, what we have done so far is we set up the parameters for the length box, we set up the parameter for cutoff length, we also look at the size of the box, we also defined if you exceed that, then what you are going to do using the logical statement if then else, and then we also looked at the time step and we set up a 0.005 of 10 to the power minus 12 second, which is we are looking at the 1 femtosecond kind of 1 or 5 femtoseconds. So, if you look at that kind of situation, now the time step is obviously created based on the two parameter for Lennard-Jonesian system sigma and epsilon. So, in this case now we are ready to give velocities. So, if you look at velocities are calculated based on of course the time step and the temperature. So, remember your equipartition theorem, we want to provide kinetic energy to all particles which are with the partition function in a way that equally distributed and in the 3-dimensional space, and those equations we already know. So, from that if you look at this 3 by 2 mv square, and if you look at that, then we are able to provide initial heat, that is based on the temperature, reduced temperature that user provided. And then once we provide that kind of potential energy in terms of the temperature, and we are also looking at half mv square. So, velocity is coming up in terms of the temperature that you are assigned here. Now, we use the shifted force potential parameters to make sure now we can provide velocity based on the differentiation of the Lennard-Jones parameter. For that, in order for us to calculate the velocity and provide that equipartition velocity, we have to now calculate the shifted force potential that gives us first differential of that is velocity. So, now we go to suppress the velocity rescaling in some cases if we want to, and then we say if number of equilibrium is equal to 0, then I flag is 1. So, that tells us whether you want to scale it or not scale it, because once you provided initial rescaling, then you let it go. You do not rescale velocities every time step, because unless you are using some kind of thermostat in order to give more potential energy to the system, but in equilibration you want to let it go and not scale the velocity, you want system to come to equilibrium by itself. So, with that understanding, now we print out our initial situations. So, we know the initial position, velocities, we know all the other parameters that we are providing in terms of time step, and all of that you know you want to print out to know what were the initial positions. So, I think that is initial parameters that we want to look at, and that is where we will look at the initial positions. So, typically initial positions are the crystalline state that we looked at earlier, or we could also have a random state where we have to be careful here, because we do not put one particle on top of the other. So, very important portion is to put them in a regular lattice structure, which is very well known in terms of crystal, and so that allows us to really understand the initial position. So, now we have finished the part of initialization of the program, defining initial velocity, positions, and all of that we are now understand very well. So, now we are ready to create the initial positions which are in face center cubic model. So, there is a FCC algorithm allows you call that FCC and the neighbor list algorithm initially, so that you understand how initial parameters are going to be provided in terms of position and also the initial neighbors. So, we will talk about that in the next section. Thank you.